power up to this stage, right? We get discuss about the second type of oscillation stability classification. So this classification is based on equilibrium imbalance. So today we will start on this. There are three types. The first type is the rotor angle stability. Actually occurs when there is a mismatch between the real power output and the generator name. That is PM and PG. Mismatch between PM and PG. It causes the rotor angle stability. Then the voltage stability. It happens when there is a mismatch between the reactive power demand and generation. That is QG and Q. And frequency stability happens when there is a mismatch between the real power demand and generation. That is PG and P. So to understand these three lines, first we have to understand this diagram. Since the figures for the synchronous machine connected to an infinite bus. You can see this component is our generator. Okay? And there are many types of generator. So this is actually the synchronous generator. Because in most practical scenarios in the large systematic systems, this type of generator is actually used. Okay? So in the synchronous generator. There is another name of the synchronous generator. And you must say that name alternator. It is called alternator, right? So what is the working principle of the generator? It will give the mechanical input heat and the output side will get the electrical output, right? So that means let's say we have some fuels like diesel, coal or etc. First we have to burn those fuels, then we will get some heat. Okay? Taking that heat, some steams are needed. Okay? And those steams, heated steams are used to actually rotate the turbine shafts. Okay? Or the turbine, there are many turbine blades. Okay? So those turbine blades will be rotating. Then the turbine shaft will be connected to the rotor of the generator. Okay? So whenever the turbine blades are rotating, synchronously the shaft will also rotate. Okay? Which will actually make the movement of rotor. Okay? So our rotor will also rotate, and the generator actually converts that rotational energy inside the rotor to the electric output power and the output side. Okay? That is the main working principle of any kind of generator. Here we can see that this is the PA or the mechanical power input that is coming from the turbine's output side. Okay? And now it is injected to the generator input side. And at the output side, we are getting some electric power. Okay? In the form of real power as well as the reactive power. Okay? So the real power generation is PG and the reactive power generation is QG. Then there is some other components here represented by this straight line. Okay, so particular straight line is okay. And you can see actually now can you see the name of these components? So which are they? Actually they are the bus bars. Okay. So what is the bus bar? Can you give any definition of bus bar? Actually, bus bar is a connection point between two components of a electric power system. Normally, electric power systems there may have different components like generators, transformers, then loads. Okay, so the connecting point is the bus. Okay, so let's say this is another network. Here we have three generators. Okay, generator 1, 2, and 3. And there are several transformers. Okay, so what is the purpose of using transformer here? Because the output that we are getting and the output side of generator is comparatively lower. Okay, if we consider the practical scenario, let's say it's actually 80 kilo. So somehow we have to step up this voltage. For that we have to use the system of transformer. Look here, this system of transformer is stepping up this 18 kilovolt to transformers. Okay. Also there are some loads here, load C, load A and load B. So to connect two components, we have to use the bus bar. Okay. Let's say this is one bus bar, this is bus bar 2. It is connecting this generator to this transformer. Okay. Then this bus bar 7, it is connecting this transformer and this load. Okay. So like this, there are many buses in the system. For this diagram, we have 9 buses. Okay. You can see the numbering of 9. Actually, with the bus bar, the one defined voltage is assigned. Okay. So let's say in bus bar 2, it has the voltage magnitude of 18 kilo. Similarly, in bus bar 1, it has a voltage of 16.5 kilo. Okay. So along with this bus bar, we will get some voltage information. So here, this bus bar is connecting this generator and this transformer. Okay. And here the voltage is V alternator. Actually, the terminal voltage of this alternator or synchronous generator.
Please slide with the slide.
This is a load. Okay, so in this load, we have to know the voltages. If you know the load voltages, then it will be easier for analysis. Okay, so actually, bus bar is not bus bar is there in the practical scenario. Maybe it is used for other purposes, like not directly, but bus bar is present in practical purposes. Generators simultaneous for any time, then it will be difficult for us to actually understand the consequences in different stability scenarios. Okay, that's why to make our analysis easier, we are considering only one synchronous generator and we are assuming the rest of the networks as infinite ones. Okay, as this is a large amount of network, so whatever let's say voltage magnitude will always remain constant in this infinite bus. Have you understood this thing? Any confusion? Actually, I am telling this thing for voltage concept for your simplicity, but in the next few minutes we will discuss that how actually our voltage and frequency are related to the reactive power and the real power. Okay. So if you have asked this question beforehand, so I am just simply telling you that this P is related to E. Okay. And here frequency is related to C. Okay. Okay. I will elaborate this things later on. So actually for this case, infinite bus, our voltage and frequency should be constant, right? That is the concept. Yeah, please. Yeah. Okay. So now, if actually we have to, if I want to say directly, I would say that if this infinite bus delivers any real power or reactive power to this generator, so the amount of real power and reactive power will not be changed inside it, right? So this is a big network. Similarly, if it takes some amount of real power or reactive power from the generator, so the difference will not be any impact on the amount of real power and reactive power that was previously given to this infinite bus. Okay. So if the real power and the reactive power inside it are remain constant, voltage and frequency will also constant. Okay. We will see the relationship between them. So have you understood this, the concept of infinite bus, and why the voltage and frequency actually are constant inside it? Any confusion? Another thing is that actually this infinite bus works as reference. Okay, so whenever we solve some numerical problems, we will set this infinite bus as reference because here the voltage magnitude is constant always. We will set it as reference, and keeping it as reference, we have to calculate the other parameters. Okay, that will be our technique. Whenever we will solve some example problems, we will see that we are making this infinite bus as reference. With the voltage, there are some voltage angles, right? So for the infinite bus, we assume that the angle associated with the voltage is zero. Okay. So with that reference, we have to calculate the associated angle with this generator, that is the delta. Okay. That means we will come in our next slide. Okay. But I just really give the introductory concept so that you can understand that what topics actually are going to be covered in this course in the future. Can actually give one practical analogy of this infinite bus so that you can understand it in a more better way. Okay? That is, let's say, let's think this infinite bus as a river, okay? And this generator as the boat. Okay? So, if the boatman takes some water from the river, so actually the amount of water in the river will be saved, right? There will be no noticeable amount of decrease, right? Inversely, if the boatman supplies some power and water from the boat to the river, so that increase will not have much indicated in the amount of water inside. Okay. Similarly, infinite bus, whether you take or give any real power or reactive power into it, or you take from it, the voltage and frequency will be kept constant. Okay. That is the main concept. Now, if you understand this diagram, now let's go back to our previous slide. Now look, the rotor angle is static. Okay. It's due to the imbalance between PM and PC. Okay. That is the real power input and real power output. So what is real power input? Right. What is actually the real power output? Okay. So ideally, this PM is equal to PC. But if there is any mismatch, so this component should be responsible for that. Let's say there are some mismatch between this PM and PC. So which one is actually the responsible? Which component here? Next to the generator. Because there is no other component except generator in this element, right? Actually, generator is the rotor because the rotor is rotating and that rotational energy is converted to the electrical energy. So if there is any disturbance in rotor movement, at that time you will see the imbalance between this EM and PG. Okay. So in the next slide we will see that how we can calculate the rotor angle. Okay. Whenever the rotor angle will be disturbed, at that time there will be some imbalance between this EM and PG. That's why it is called the rotor angle stability. Okay. Any confusion? Now let's go to the voltage stability. Okay. It is the imbalance between the reactive power generation and reactive power demand. So this is the reactive power generation. This is the reactive power demand. This is the real power. If there is any mismatch between this Q and this QG, okay, so we are calling it as voltage stability. Why? Because the mismatch is for reactive power Q, but we are referring it to voltage stability or voltage stability because actually this Q and V are actually strongly coupled to each other. Okay? So if actually Q increases, then V increases. Okay? You should know this thing from your house diagram. Okay? Whenever Q increases, V actually increases. Okay? There is one simple formula that actually gives us the relationship between V and K. That says that V equals to V naught plus KV. Okay? So here V naught is the lower voltage, V is our voltage, and here Q is the reactive power. This K is a positive constant. Okay? That means that whenever this formula is cross sign, whenever this Q will increase, the V increases, right? If Q increases, V also decreases. Okay? So can you relate the Q with G? Okay? So that's why the infinite class I was taking that the amount of power, reactive power will be same. That's why the voltage magnitude will also be same. Okay? So if the reactive power generation and demand do not match, at that time we will call it as voltage stability scenario. Okay? Then the last case is the frequency stability. So there is any mismatch between the real power demand and generation. That is the PG, is PG, real power generation, and the real power demand P. If there is any mismatch, we will call it as frequency stability because similar as Q and V, here P and F frequency are actually strongly coupled and there are some relationships. Okay? If P increases, F also increases. If P decreases, F decreases. Okay? So that's why the mismatch is for the real power demand, but we are calling it as frequency stability or frequency stability scenario.
Sir, how is frequency related to the real power?
How?
Is frequency related to the real power?
Real power. So there is one formula that I use there is some formula like this that change in frequency which is proportional to the change in real power, and there is one parameter that will be handled like this. So using this formula actually the frequency changes in terms of real power. Okay. But as well as from the house diagram you can also observe this thing. Okay. Whenever the real power decreases, the frequency decreases. So I think we can again go to the house diagram of that. At that time we really understand the relationship between P and Q as well as the P and Q. Okay. So any other questions? This diagram is called the single line diagram. And in this course, our 90% contents will be based on this diagram. That is the single machine connected to infinite bus. This system is called single machine infinite bus system. Shortly, SMIB system. We will see this in our next slide as well. This is called the single machine infinite bus system. And then there is one slide where actually we will study about the two machine system. So if we increase the number of machines in our study, then there will be obviously some complexity. Okay? So we will also go through that slide that the two machine systems, but except that effects or the consequences of stability. Okay. Otherwise, we will not realize the importance of stability. Okay. So let's say this is a network diagram. Okay. Here actually you can see there are three generators, right? There one, this is two. From the number of generators, actually it is called the gate machine system. As there are three generators, we will call it as three machine system. And here the number of buses are 9, so we will call it as 3 machine 9 bus system. Okay. So I have already discussed about the bus and also about the transformer. This is the transformer. Okay. We know this parameter. So this is the transformer reactance, like J.06. This is the bus voltage. Okay, like this. Now look, this is the transmission line. So here something is written over here, right? 0.0085 plus J.07. The first portion is the reactance resistance, and the next portion is the reactance. Okay, comparing this model with our impedance. Then there are something written over here. This is the B value. Okay, you know what is B? What is B? This is the transmission line properties. So these are the properties of transmission lines: resistance, reactance. Is it any other thing like weight?
ABCD parameter. There are some parameters ABCD.
ABCD parameters is another thing, but this is related to resistance, reactance, kind of these things. Maybe you say that susceptance, right? Yeah, this is the susceptance, shunt susceptance or shunt capacitance. Okay, this is actually the shunt capacitance B. But why we divided it by 2? Any idea?
So there are some concepts for long transmission and medium transmission. We lump them together and
Exactly.
divide them by 2.
So actually in your power system course, maybe you have learned that there are some classifications of transmission lines in terms of length. Okay, like short transmission line, then medium transmission line, and long transmission line. So for the short transmission line, the assumptions are that we actually created the resistance and reactance. Okay, so we do not care about the resistance and reactance. We only care about the shunt capacitance. For the medium line transmission line, actually this diagram is for the medium line transmission line, where the transmission line length may be in the range of 20 km to 85 km. At that time, we have to consider the resistance as well as the reactance, okay, and also the shunt capacitance. And for the medium line transmission line, there are two models, I model and G model. Okay, so in those two models, actually, it is assumed that our shunt capacitance will be split into two portions, and one portion will go into the sending end, and one portion will be allotted for the receiving end. Okay. Whenever we will do the load flow of this diagram, let's say we know all the voltages here and all the parameters, so we can run the load flow analysis, right? So after the load flow, what will be our solution? We will get some power flow direction, right? With the amount of power that are actually coming out or coming in to any class, right? Or to any class. Let's say this is the directions. Okay. Here all the directions and the arrows that I will write here. So this is just the arbitrary arrows of directions. Okay. This is not the calculated directions. So let's say this is the scenario of our power flow solution, and this is the directions. So either depending on the power flow solution, either this line will be sending in or receiving end. Okay. So it will be only one, either sending end or receiving end. That's why here it is denoted by D by. Okay. Here also it is D by. Across all transmission lines, here D by is denoted. And for the long transmission lines, actually the calculation is difficult. We will not go into that. Okay, so this is our network. So there are another thing, the load. Okay, so there are 3 loads. Load C, load B, and load A. There are 3 loads. Okay. So this is HV machine, 9-bus system. So we have transformers, transmission lines, and then actually load. Okay. That three buses, bus 8, 5 and 6. Now another thing, actually here all the resistance, reactances and the shunt capacitors are lumped into a discrete point. Okay. Have you ever heard about the term lump? Do you know the lump network? What is meant by this lump network? Can you know that?
Consider all the parameters in a single point instead of dividing them.
Yeah, exactly. You are almost right. You are fully. So in the circuit boards, we use some this type of circuit. Yes, in a single circuit. So we have to go into this is the transmission line, right? If I want to say that is there any voltage difference between these 2 points, we will say that no, right? Assuming that there is no resistance here, right? But think about one transmission line. So inside the transmission line, the resistances or reactances or shunt capacitance, all the terminals should be distributed over the line continuously. It shouldn't be at some point and then shouldn't be present at another point. Not like that. Rather, the transmission line should have the resistances, reactances over the line, okay, continuously. But for our calculation to make it easier, we consider that we actually consider it as lump network. Lump we put it together into some discrete points. Let's say there are resistances across the transmission line, but we are actually thinking that okay, so 2 ohm is here only in this discrete point, then 3 ohm is here, and in other lines there are no resistance or reactance because we have actually marked all the resistances into these 2 discrete points. Okay, that is the concept of lump network. Have you understood this thing? So actually here as well, as though the resistances, reactances are distributed over the line, but it is considered as lump network. That's why all the resistances, reactances are here in this portion. Okay. So now I think we have described this diagram. Now let's go to the consequences of stability. Okay. Let's say we have load demand here of 100 kilowatt. How to satisfy this load demand by these components? By these 3 generators, right? Let's say this generator is providing 40 kilowatt supply, and from this generator we are getting 80 kilowatt supply. Let's say from this generator we are getting 80 kilowatt. 80 plus 80 plus 40, so 200 kilowatt load demand are being satisfied. So, and these 3 generators are the synchronous generation, right? So, synchronous generator runs at synchronous speed. That is represented by ns. Okay, ns. And there is one total formula for ns. That ns will be equal to 120 divided by 3, right? It is the number of poles and this is the nominal frequency at which the generator is operating. System is operating. For our countries, 50 hertz. Maybe for other countries, it may have 60 hertz. Okay. So let's say there is some disturbance in the rotor angle of this generator 2. Okay. And for that reason, this generator 2 is not running at synchronous speed. Whether it is running at different speed and continuously it is changing its speed. Okay. That is the actual dynamic. It is going to the dynamic state. Okay, stable state. Okay. Now, remember that across each of the component there are some protective equipment like cables or circuit breakers. Okay. So whenever there is any fault in a particular component, what will be the first task of the protective equipment and it was to isolate that unhealthy part from the healthy portion of the network, right? So there are some protective equipments here, right? So whenever there is some disturbance in the rotor angle of the generator flow, so the protective equipment associated with the generator will immediately disconnect this generator from the system. Okay? Now this generator is disconnected from our system. Okay? And this sudden disconnection is called as generator tripping. Okay? So what is tripping? Tripping is the sudden disconnection from the network due to a fault, due to a disturbance. Okay? So this is the generator tripping. So we have understood the first consequence, right? So our circuit generator will be tripped. Then let's say due to the disconnection of this generator, we will have the deficit of this particular one, right? That was generating or supplying from this generator. But our load demand is still 200 kilo. So what can be the probable solution? How can we meet the load demand? Yeah, loading is one scenario. This is the last solution. Whenever we are not capable to do any kind of solution, we will share some amount of load from the system. But should we have any other options? Because there are two generators, right? So we can increase the supply power from these two generators, right? So this can be the best option. Okay. So let's say I am giving extra 20 kilowatt generation from this generator as well as 20 kilowatt from this generator. Okay. So now the load demand and total generation is same, right? 200 kilowatt. Now, before the fault phase or in the pre-fault scenario, this generator was providing 40 kilowatt. This was and this was 8. At that time, we can solve the load flow, right? We will get some power flowing across any transmission lines, okay, with its duration. We will get that information. Let's say at that time, the power flowing through this transmission line is 20 kilowatts, okay. And after fault, now this generator is disconnected, and this amount of power is delivered now by sharing of these two generators by 20 kilowatt and 20 kilowatt, okay. Now we can again solve our load flow, right? And now we will get a new set of solution, right? We will get an updated power flow, right? Okay. So that's why our power flow is ampered. Okay. This scenario is called the ampered power flow, because due to the new scenario, we have to again calculate the load flow and the power flow will be updated. Okay. So this is called the ampered power flow. So due to this ampered power flow, let's say previously in the pre-fault case, this line was taking 20 kilowatt, okay, and after the fault, actually now in the updated power flow solution, you are getting, let's say, this all are actually this all of these values are actually identical. Okay, so you know, take these values as calculated values. Okay. Let's say in the post-fault scenario, now the updated power flow solution gives us 20 kilowatt power flowing through this transmission line. Okay. Now for each transmission line, there is a limit of power flow. Okay. So let's say the limit for this transmission line is 22 kilowatt. That means it can take up to 22 kilowatt power flow. Okay. If the power flow is beyond that, this transmission line will not be capable to take that. Okay. So now the power flow is 25 kilowatt. So what will be the scenario? What will be the consequences? This line will be broken. Okay. This line actually can take this high amount of power flow. So it will be broken immediately. So if this line is broken, then the bus 8 and the bus 7 will be disconnected, right? Because this was the connection. So these two will be separated. Now, if this generator 1 wants to supply the power at load C, previously maybe there was two paths, right? This can reach the power supply to this load using this one. Okay. So it may happen that again this transmission line may be overloaded, right? Because all the power flowing is now occurring through this line. So if again this is overloaded, then this line will be broken down. So load C is now completely disconnected from the generator sources, right? So there will be some outage or load shedding here. Outage is the complete load shedding. There is no supply provided to any particular load demand. That is called the outage. Okay. So this line is broken. This is now in the outage signal. If this line breaks actually, okay, then there will be new set of powerful solutions, and at that solutions maybe some other lines will be overload, right? So let's say all of these lines are breaking. Okay. So this phenomena is called the cascaded outage. So what is the cascading? Cascading means that one event is relevant to the previous event. Actually, one event is occurring due to the previous event, then another new event will be occurred due to the previous event, like this. Okay. So as one transmission line is breaking down, then after that others are also breaking down. So this scenario is called the cascaded outage. Okay. So this point is clear to you, right? Any confusion up to now?
So if the transmission is broken, how will the power?
No, only this line is broken. Okay. Then there is the rest of the network. Yeah, then there will be no power, right? Going to that one. Okay. So if like this way all of the transmission lines are breaking down, then all this load A and load B and load C, okay, will go to the outer system. Okay. So in the system there are only 3 loads, but no supply, right? So this system is called the system blackout. Okay. The system blackout is as all the lines are breaking down, like this load C, load B and load A will not also make any power supply for the generator, right? So all the load demand 200 kilowatt, all load demand should be now on the ground. No power supply is given to the any of the load. Okay, that's why this is called the system blackout. It is system blackout. Now if this system have you understood the cascade outage?
System blackout చేయటం
set of solution for power flow. We are getting that we are seeing that this line is broken due to the overloading condition, right? So what this another line will be overloading, right? It will be disconnected. Like this way, all of the transmission lines will be getting okay. So that's why load C and load B and load A, all the loads will go to the complete load sharing scenario. Okay. There will be no power. There will be no power in any of them. Okay. This scenario is called the system blackout. So whenever system blackout happens, obviously the system reliability reduces, right? Because let's say if DC and DESCO are the power system provider, if they can provide power to the customer continuously and smoothly, then actually obviously their reliability will reduce, right? That's why another consequences is that the system reliability reduction. Okay. So we have discussed these 6 points. If you have any questions up to now, you can ask.
So what is the difference cascade outage and system
Blackout. Cascade outage is actually one kind of phenomena that for one transmission line is getting overloaded, there are other transmission lines which will be affected, and gradually those lines will be overloaded and those lines will be in the those lines will be disconnected. Okay. So this phenomena is called the cascade outage. So if the cascade outage occurs and all the transmission lines are actually broken down, at that time all the loads will be in the outage condition, and that phenomena is called the system blackout. System blackout means in this system
further transmission means the line should be
Yeah, the line should go always the line.
Yan siya, Tripoli Nisila. Tripoli Nisila.
Though these scenarios are very honest, actually if actually this limit actually exceeds, then this line degree damage means it will be very easily done. We have to actually replace this. So any other questions up to now? If the system lagged out occurs, so as a customer we will not happy, right? So the power system provider, let's say this for UPC or this for another power system providers present in our country, for them the reliability will reduce, right? So this is actually a reliability issue, right? If we are not getting proper power supply from the provider, then what is the reliability? Okay? That's why I say that this is the system reliability reduction. So if you do not have any question, I am giving you 2 minutes today. You can process the things that I have discussed. Okay? And in these 2 minutes, I will take your attendance. Some students are joining late. I have observed in other sections as well. Maybe sometimes I will take the attendance at the beginning of the class.
বুঝা যাবে নামলেও আমি হলো ডাইরেক্ট চলে যাবো না আমার এরকম এখান থেকে নিচে রেখে আসছি হলের নিচে
4, 5, 6, 7, 8, 9, 10,
Yes, sir.
11,
Yes, sir.
12,
Yes, sir.
13,
Yes, sir.
14, 17, 18,
Yes, sir.
21, 22, 23, 24,
Yes, sir.
25,
Yes, sir.
26,
প্রেজেন্ট স্যার
27, 28, 29, 30,
Yes, sir.
31,
Yes, sir.
32, 33,
Yes, sir.
34,
Yes, sir.
36,
Yes, sir.
37,
Yes, sir.
38,
Present, sir.
39,
Yes, sir.
40,
Present, sir.
41,
Present, sir.
42,
প্রেজেন্ট স্যার
46, 47, 48, 49, 50, 51,
Yes, sir.
52,
Yes, sir.
53,
Yes, sir.
54,
Yes, sir.
55,
Yes, sir.
56,
Yes, sir.
57,
Yes, sir.
58,
Yes, sir.
59, 60,
Yes, sir.
62,
Yes, sir.
64, 65. Yes, what about this point? What is up to now, we have only considered the real power demand and real power generation. As well as there we have some reactive power demand and some reactive power generation from the generator. Let's think about industry of factory. In the big industry or factory, loads are the inefficient because there are many industrial motors and fans, fans, conveyor belts. This type of things actually are consuming inductive power from the system, okay? And they are actually the inductive load. So there should have some reactive power demand in your system, okay? And let's see that there will be some QG or the reactive power generation from the generator, okay? Whenever we discussed about the real power issues, our generator was some transmission line failure. So it will not be possible to meet the reactive load demand completely, right? So if there is any mismatch between the reactive load demand and the reactive power generation, at that time our voltage will collapse. Because we have already studied that our P and Q are actually related, right? So if there is any mismatch between the reactive power generation and demand, then it will affect the voltage profile. Okay. If you do the calculation in per unit, you know that 1 per unit voltage is the ideal case, but there are some allowable limits. Right? If our voltage profile remains in this range from 0.9 per unit to 1.1 per unit, then we can take it as safe operating limit. But if somehow our voltage profile gets below this 0.9 per unit or above this 1.1 per unit, at that time we can think that our system voltage can be collapsed in waves. Okay. So this is actually the voltage collapse. Actually, this is the voltage system. Okay. Same thing. Whenever there is a mismatch between the electric power demand and the generation, that is the AC and Q. Then the system frequency variation. So we know that frequency is related to the real power demand. So if there is any mismatch in real power demand and real power generation, at that time the frequency will either increase or decrease, right? So there will be some frequency variation. So this is here, this is this type frequency is timing. Okay. So if the frequency varies, what will be the effect? Okay. So let's take one example. Let's think about one cold links or beverage company. Okay. In this type of companies, there are like this mechanism. Let's say this is one pipe. Okay. There are some openings or nozzles. Yeah. Okay. Then below there are conveyor belts. Okay. So there are some wheels which are operated by wheels, and this conveyor belt actually is operated by the industry. Okay. And let's say there are some bottles here.
study the voltage stability and the frequency. Okay. Because these two topics are
these two topics are actually studied in the MSc or PhD level courses. Okay. We will only discuss about the total angle stability. And what is total angle stability? We will have two types of disturbance. One is small disturbance and another is large disturbance. Small disturbance means steady state stability, and it means the transient stability. Okay. So the last class I already discussed about these two types. So in the next slide, we will study about the origin of the synchronous machine. Okay. Then in slide 3, we will talk about the small disturbance stability or steady state stability. They are actually we will only consider the total angle stability. Okay. We will not consider about voltage stability or frequency stability. Then in slide 4, we will study the transient stability. Okay. So the large stability. There also we will assume that as total angle stability. Okay. And then we will study about the two machine system. So that will actually cover our course content. There will be only one remaining, that is called the economic load distance. Okay. So what is this? Load distance means load distribution among different generators. Okay. So let's say here the total load demand is 20 kilowatt. So from which generator you want to take how much amount of power? That should be your function, right? So if you can operate it or if you can do it in a most economic way, then you can save the operational cost, right? So your total generation cost will be minimized. That is your main target. Let's say you are owner of a power producing company. Okay. So you buy fuels from outside, you burn those fuels, and you convert the mechanical energy to the electrical energy in the generator. Then you actually sell those electric energy to the market. Okay. Then your target will be to minimize the generation cost. Okay. So each of these generators have some fuel cost coefficients. Okay. So it is actually varied from generator to generator. So let's say this generator 3 has the higher fuel cost coefficients, and this generator 1 has the lower fuel cost coefficients. So your target will be to produce as much power possible from this generator 1, right? So let's say your demand is 200 kilowatt. So you want to get from the complete 200 kilowatt generation from this generator 1, because here the fuel cost coefficient are less. Means that to produce 1 kilowatt energy, it will produce it at a cheaper rate than this generator. Okay. But there are some limitations or constraints. So in the power system optimization terms, we will say these things as constraints. Like there are some minimum and maximum limit of generation for any generator. Let's say the maximum limit of generation for this generator is 100 kilowatt. So, okay. Though the load demand is 200 kilowatt, you can supply more than 100 kilowatt from the generator. Okay. So there are some constraints or limitations. Okay. So there are other constraints like you have to somehow match the total generation with the demand as well as the loss. That means your generation should be equal to the demand plus loss. Okay. Then there are some equations. For this, there are some inequality constraints. Okay. So for 3 generators, there will be 3 inequality equations. This is 1 equality equations. Okay. Then you have to solve. Okay. After solving, you will get the optimized load dispatch. Okay. From this generator, we can supply this amount of power. And for this is the actually most economic factors where we can actually minimize our total generation cost. Okay. So this will be discussed in a separate slide on the ELT of the economic load dispatch. Okay. So I am just giving you the essence of the course contents that we will cover in this semester. Okay. So I think we can conclude